everyone, a warm welcome. Today I am going to solve part A of our model question paper.
Our first question is, derive a partial differential equation from the relation z equal to f of x plus 80 plus g of x minus 80. See, our question is formation of partial differential equation from z equal to f of x plus 80 plus g of x minus 80. Here, f and g are two arbitrary functions. So, we can form a partial differential equation by eliminating the arbitrary functions f and g. See, f and g are functions of x and t. So, we can think z as a function of x and t. See, here z is a function of x and t. So, we can differentiate z partially with respect to x and partially with respect to t. See, these are its first order partial derivatives. And its second order partial derivatives are dou square z by dou x square, dou square z by dou t dou x, dou square z by dou t square. They are denoted by r, s, t. Let it be equation number 1. You differentiate 1 partially with respect to x and t. So, dou z by dou x, that is p is equal to, you differentiate partially with respect to x, f dash plus g dash. Next, you differentiate partially with respect to t, that is q is equal to f dash into derivative of x plus 80, that is a. So, a into f dash. See, while evaluating p, here f dash into derivative of x plus 80 with respect to x, it is 1. So, you have to multiply by 1. So, there is no change. That's why it is f dash plus g dash. So, q is equal to a f dash minus a g dash. Next, you try to eliminate f and g. Here, in p and q, you can see derivatives of f and g, that is f dash and g dash. Next, you try to eliminate f dash and g dash from these three equations. Equation number 1, 2, 3. You can see you can't eliminate f dash and g dash from these three equations. So the elimination is not possible. So in such situations, you have to find r, s and t. Then you try to eliminate, you can make a partial differential equation. What is r? R is dou square z by dou x square. You differentiate p with respect to x. Again f2 dash plus g2 dash. Next, s. For getting s, you differentiate 2 partially with respect to t. Derivative is f2 dash into a minus a into g2 dash. What is t? T is you differentiate 3 partially with respect to t. F dash is f dash of x plus 80, g dash of x plus 80. That is, t is you differentiate with respect to t again. So, a square f2 dash minus a g dash of x minus 80 minus a g2 dash into minus a, so plus a square. Next, you try to eliminate the arbitrary functions from equations 1, 2, 3, 4 and 5. See, by looking into these equations, you consider equation number 4 and 6. See, this is a square into f2 dash plus g2 dash. By equation number 4, it is a square into r. So t is equal to a square into r. See, this is the required partial differential equation. See, it is an equation containing partial derivatives r and t. And this equation is independent of the arbitrary function. So this is our required partial differential equation. Second question is solve dou square z by dou x dou y is equal to x square y. See, in this partial differential equation, there is only one term with the partial derivative. So we can find its solution by direct integration. What is dou square z by dou x dou y? It is dou by dou x of dou z by dou y. So first you integrate with respect to x. Integrate with respect to x. What is left side? Dou z by dou y is equal to, we are integrating with respect to x, so x cube y by 3 plus, after integration we have to put a constant. Here the constant is a function of y, right? Because while differentiating partially with respect to x, we kept y as a constant. So in our constant, y may appear. So the arbitrary constant is function of y. Again you integrate with respect to y. That is left side, it is z. Z equal to x cube y square by 6. See, for integrating this, you have to keep x as a constant. So x cube by 3 is a constant. That is integral y, it is y square by 2. So y square by 3 into 2 is 6. So the term is x cube y square by 6 plus. We are integrating with respect to y. What is integral fy? It is integral of fy dy plus. After integration, we have to put a constant. See, that constant is a function of x. Because while differentiating with respect to y, we kept x as a constant. So here the integrating constant may contain x. So we can consider it as g of x. See, this is our solution, this section. Again, we can see, this is again a function of y. Let it be f of y. So it's equal to x cube y square by 6 plus fy plus gx. So you can write the solution as z equal to x cube y square by 6 plus fy plus g of x. Question number 3. State any 3 assumptions in deriving the one-dimensional wave equation. During the derivation of wave equation, we made few assumptions. Assumptions are, number 1, the string is made of homogeneous material. That is, mass per unit length of the string is a constant. Number 2, the only force acting on the string is its tension and it is very large. Number 3, there is no effect of gravitational and external forces. Number 4, the vibration takes place in a plane and small. Number 5, there is no horizontal displacement. Question number 4, what are the possible solutions of one-dimensional heat equation? See, there are 3 possible solutions of the one-dimensional heat equation. The 3 possible solutions are, number 1, u equal to C1 e raised to px plus C2 e raised to minus px into C3 e raised to c square p square t. Number 2, u is equal to C1 cos px plus C2 sin px into C3 e raised to minus c square p square t. Number 3, u is equal to C1 plus C2x into C3. See, these are the 3 various possible solutions of the heat equation. Or you can write these 3 possible solutions are, see, this is equivalent to, this is also equivalent to, u is equal to, you consider C1, C3 as an arbitrary constant A, again C2, C3 as another arbitrary constant. So you can write, see, u equal to A e raised to px plus b e raised to minus px into e raised to c square p square t. Again, this equation can be written as u is equal to a cos px plus b sin px into e raised to minus c square p square t. This can be written as a plus bx. It's not necessary for rewriting these solutions like that. Fifth question. If f equal to u plus iv is analytic, show that u and v are harmonic functions. See, how to remember that? If f equal to u plus iv, then its real and imaginary parts are always harmonic functions. See, in this question we have to prove u and v are harmonic functions. For proving, you have to establish this equation: dou square u by dou x square plus dou square u by dou y square equal to 0. Then we can say u is harmonic. In order to prove v harmonic, you prove that dou square v by dou x square plus dou square v by dou y square equal to 0. So our aim is to prove these two equations. Given f equal to u plus iv is analytic, so we can say u and v satisfies Cauchy-Riemann equations. What are Cauchy-Riemann equations? Dou u by dou x is equal to dou v by dou y, and dou u by dou y is minus dou v by dou x. See, these are Cauchy-Riemann equations. With the help of these two Cauchy-Riemann equations, we can prove u and v are harmonic. See, for proving u harmonic, we have to prove dou square u by dou x square plus dou square u by dou y square equal to 0. Here we have dou u by dou x. For getting dou square u by dou x square, we have to differentiate one partially with respect to x. So dou square u by dou x square is dou square v by dou x dou y. Next, we have to find dou square u by dou y square. For that, you differentiate equation number 1 partially with respect to y. So dou square u by dou y square is minus dou square v by dou y dou x. Now we have equations 3 and 4. You consider equation 3 plus 4. 3 plus 4 implies dou square u by dou x square plus dou square u by dou y square is equal to dou square v by dou x dou y minus dou square v by dou y dou x. We know these two are equal. See, dou v by, you consider dou v by dou y. If you differentiate dou v by dou y with respect to x and dou v by dou x with respect to y, both these two second order partial derivatives are same. So these two are same. So it is 0. So we have dou square u by dou x square plus dou square u by dou y square equal to 0. Hence, we can say u is harmonic. Similarly, we can prove v is harmonic. That is, we have to establish this equation. So we have to find dou square v by dou x square. For that, you differentiate 2 partially with respect to x. That is, dou square u by dou x dou y is minus dou square v by dou x square, which implies what is dou square v by dou x square? It is minus dou square u by dou x dou y. Next, you differentiate 1 partially with respect to y. While differentiating 1 partially with respect to y, we will get the term dou square v by dou y square. We need dou square v by dou x square and dou square v by dou y square. Already we have dou square v by dou x square. Now we need dou square v by dou y square. For that, you differentiate 1 partially with respect to y. We have, it is dou square v by dou y square. It is dou square u by dou y dou x. So now we have equation number A and B. You consider A plus B. It gives dou square v by dou x square plus dou square v by dou y square is equal to, it is minus dou square u by dou x dou y plus dou square u by dou x dou y dou x. See, both are same, is equal to 0. So we have dou square v by dou x square plus dou square v by dou y square equal to 0. So both real and imaginary parts u and v are harmonic. Sixth question is, check whether f is z equal to z conjugate is analytic or not. See, any function containing conjugate is nowhere analytic. That's the result. From this we can conclude it is not analytic. But in this question, you have to check whether f z is analytic or not. For that, you check whether f satisfies Cauchy-Riemann equations and the four partial derivatives are continuous. This is the method. For that, you express f in the form u plus iv. What is z conjugate? Z is x plus iy. Z conjugate is x minus iy. See, it is in the form u plus iv. What is u? U equal to x. V is equal to minus y. Next, what is ux? It is 1. Uy, it is 0. Vx, 0. Vy, minus 1. Ux not equal to Vy. So we can say it is not analytic anywhere. That is, it is nowhere analytic. Seventh question is, evaluate integral over c tan z dz, where c is the unit circle. See, you can evaluate this integral by residue theorem. So let f is z equal to tan z. You identify its singularities within C. For getting its singular point, you write tan z as sin z by cos z. So singularities of f z are those values of z which satisfies cos z equal to 0, which implies cos z equal to 0 when z equal to, we know, cos pi by 2 is 0, cos minus pi by 2 is 0, cos 3 pi by 2 is 0, cos 3 minus 3 pi by 2, etc. 5 pi by 2 minus 5 pi by 2, etc. equal to 0. So the singularities are pi by 2 minus pi by 2, 3 pi by 2 minus 3 pi by 2, etc. Next, you identify its position with respect to the circle C. See, pi is 3.14 by 2. See, our circle is unit circle. So clearly all the singularities are outside of C. No singularity lie within C. So here all the singularities are within C. That is, f has no singular point within C. That means f is analytic within and on C. So by Cauchy's theorem, integral over C f is dz is 0. See, in residue theorem, if all the singularities are outside, there is no residue, and again integral over C f is dz is 0. Or you can directly apply Cauchy's theorem. So value of the integral is 0. That is our f is z is tan z dz. Question number 8. Find the Taylor series of f z equal to 1 by z about z equal to 2. You are familiar with the Taylor series of f z at a, and it is f z equal to f of a plus z minus a into f dash a plus z minus a the whole square into f2 dash a by 2 factorial plus z minus a the whole cube by 3 factorial f3 dash a plus etc. See, this is our Taylor series expansion of f z at a. See, in this question, f z is 1 by z and a is 2. You write the successive derivative of f. For writing the successive derivative of f, you write 1 by z as z raised to minus 1. So what is its derivative? We know derivative of x raised to n is nx raised to n minus 1. So its derivative is minus z raised to minus 2. Next, f2 dash z is 2 is z raised to minus 3. f3 dash z is minus 6 is z raised to minus 4. So if you rewrite 1 by z as z raised to minus 1, then you can easily write its successive derivatives in this way. Then what is f2? f2 is 2 raised to minus 1, that is 1 by 2. f dash 2, it is minus 2 raised to minus 2, that is minus 1 by 4. f2 dash 2 is 2 by 2 cube, that is 1 by 4. We have 3 non-zero values, that's enough for writing the series. So there is no need of finding f3 dash 2. You put these values in equation number 1. So we have f is equal to fa half minus z minus a into 1 by 4 plus, sorry, what is a? You put the value of a is 2. Z minus 2 the whole square by 2 factorial. f2 dash 2 is 1 by 4 minus etc. That is f is equal to half minus 1 by 4 into z minus 2 plus 1 by 8 into z minus 2 the whole square minus etc. This is the Taylor series expansion of f z at the point 2. See, our ninth question is, what type of singularity have the function f is equal to 1 by cos z minus sin z? You can find its singular point by solving the denominator equal to 0. That is cos z minus sin z equal to 0. Which implies cos z equal to sin z. Next, for identifying the singular point, you divide either by cos z or sin z. If you divide by cos z, we have tan z. If you divide by sin z, we have cot z. But we are more familiar with the tan z, so divide throughout by cos z. Dividing by cos z. So 1 is equal to tan z. Which implies tan z equal to 1. So what is z? For which value of tan is 1? We are familiar with 5 by 4. So tan z equal to 1 implies z equal to 5 by 4. So by solving this equal to 0, we have z equal to 5 by 4. So its only singularity is 5 by 4. Clearly, it is a pole. So its singularity is 5 by 4 and it is a simple pole. Then the question is, find the residue of e raised to z by z cube. Let f is equal to e raised to z by z cube. Clearly, 0 is its singularity and it is a pole of order 3. We have to find a residue of f at 0 is equal to, see, it's pole of order 3. What is its residue? See, z equal, we know the result. If z is a pole of order n of f is z, then residue of f at a is 1 by n minus 1 factorial. Limit z tends to a, n minus 1th derivative of z minus a raised to n into f is z. See, this is a residue. Here, n equal to 3. So what is the result? 1 by 2 factorial. Limit z tends to a, second derivative of z cube f is z. See, this is the result. So it is 1 by 2 factorial, limit z tends to 0, second derivative of z cube into f is z. What is f is z? It is e raised to z by z cube. This will cancel each other. You can see this 1 by 2, limit z tends to 0, second derivative of e raised to z. First derivative is e raised to z, next derivative is also e raised to z. So it is e raised to z. That is 1 by 2 into, when z tends to 0, e raised to 0, it is 1. So the answer is 1. So the residue of f at 0 is half. See, there is one more method of finding its residue since f z contains e raised to z. The alternate method is you write its law in series expansion. That is, you express f z in the form of an infinite series. We can express in the form of an infinite series because we know the infinite series expansion of e raised to z. So what is f z in the form of an infinite series? So e raised to z is 1 plus z square by 2 factorial plus z cube by 3 factorial plus etc. The whole divided by z cube. That is 1 plus 1 by z square plus 1 by 2 factorial into z plus 1 by 3 factorial plus etc. See, clearly this infinite series containing only positive powers of z. See, this is the Lorentz series expansion of f z. Clearly 0 is the singular point and its residue is that is residue of f at 0 is the coefficient of 1 by z. So we have residue of f at 0 is coefficient of 1 by z. What is the coefficient of 1 by z? It is 1 by 2 factorial, that is 1 by 2.